Welcome to our third portion of session 12 on beams. And this is our final portion of the session. We are going to continue to discuss how we might plot or graph bending moments and shear forces along a beam that's transversely loaded. And now our topic of discussion revolves around what happens if there is an applied force or an applied moment at a specific location. These applications of forces or moments are actually discontinuities as we go along the beam. So we want to ask ourselves a couple of questions. One is, what happens when we encounter a concentrated force or discontinuity in applied force? Something like what we see here. We're moving along the beam, and all of a sudden, whoop, there's an F app. So what we're going to derive in a few minutes is how this internal shear force changes as a function of F app. And the spoiler is the change in the internal shear force is equal to F app. Another question we'll answer is what happens when we encounter a concentrated moment? We have a discontinuity in applied moment as we move along the beam. And so here we have another beam. We're moving along in X. We hit this applied moment and ask ourselves, how does the internal bending moment change as a function of this applied moment? And the answer is similar. Delta M is equal to M app. Okay? And we asked the question, how does internal shear force vary with an applied force? Okay. But we can also ask the question of, wait, how does the internal bend moment vary with an applied force? Or how does the internal shear force vary with applied bending moment? Okay. So we'll do these derivations now to cover what's happening. Let's look at the case where we have a concentrated force. What happens when we encounter this concentrated force? We're moving along, there's F app, and we want to know, okay, what was going on just before we got there and what was going on just after. So let's take an element that kind of just encompasses this F app, and we'll say that this element has the applied force and it has a very small width, delta x. And on the left side, we'll put an internal shear force and a bending moment. And on the right side, we'll say there's a shear force with a slightly augmented delta V, okay, with a slight change in it because we've moved a slight amount, delta x. And also similarly, there's an internal bending moment, and that can also change slightly as we've moved a small amount, delta x. So what do? Well, we once again apply Newton's second law, and we say that we're going to look at the forces in the vertical direction, set them equal to 0. And when we do that, what do we have? We have a v, right? And we have a v plus delta v. And we also have an F app. We don't need to worry about the bending moments. So we have v minus this quantity, v plus delta v plus F app. The v's cancel out, and we have a minus delta v plus F app is equal to 0. So delta v is equal to F app. Now, that's the relationship that we had shown on the previous slide. It was wonderful. And now let's just check out what's happening with the bending moments. So we can sum the bending moments at some location, say O here. And when we do that, we say that we have contribution from M, we have a contribution from M plus delta M, okay, and this contribution is negative, so that's the minus M that you see here. This contribution is positive. We also do have a contribution from F app, Okay, it's a distance delta x over 2 away from O, and it is positive in nature. Nonetheless, we're going to say that this delta x over 2 is very small. This is a very narrow element. And so we're going to neglect its contribution. And we're going to say that the change in the moment due to this applied force is going to be 0. So the takeaway here is that the change in internal shear force is equal to the applied force, F_at. And notice that F_at is in the positive y direction, and the change in the shear force, internal shear force, okay, so if I'm going from here to here, is also in the positive direction. Now, let's take a look at what happens with a coupled moment. We are moving along in the x direction. As we see here, we have our applied moment, mmap, there. And it's actually in the minus z direction. So z is coming out of the page, and mmap is going into the page. Once again, we draw a box, or we make an element surrounding this mmap. And we say it has some width delta x, and the applied moment is, is on top of it. Excuse me. So on the left side, we can once again put a shear force, internal shear force, and an internal bending moment. And on the right side, after we progress some amount delta x, we can say, hey, it's changed just a little bit. So v plus delta v and m plus delta m. We do the algebra associated with equilibrium for the forces. So the sum of the forces in the y direction is going to be equal to 0. What are our forces? Just v and v plus delta v. So we write them out and we set them equal to 0, and we get delta v equals 0. Now, let's look at what's happening with the bending moment. To do this, we go ahead and select a location. We'll say it's going to be on the right side here, and we'll call that point O. What's contributing to a resultant bending moment here? We have this m, we have this v, okay, acting at a distance delta x in the negative direction, okay, it's going into the board. We have mmap also going into the page, and then we have no contribution from v plus delta v and m plus delta m right here. And we set all that equal to 0. So we see m or minus m and m, they cancel. We see that we have mmap, and we see we have delta m, and then we have this minus v delta x. So we can write out the change in moment is equal to mmap plus v delta x. And what do you think we're going to do? We're going to say that delta x is small, and therefore we can say that delta m is about equal to the applied moment, and this is the equation we want to take away from this derivation. Notice this applied moment is negative, but the change in internal bending moment ends up being positive. And the math and the equilibrium and our diagram display this, but it's something to keep in mind when we're not going to do this derivation every time. We're just going to apply this equation. This is contrasting to what we saw when we were looking at the applied force, which was in the positive direction and resulted in a positive change in the internal shear force. Well, let's do an example. Here, what we have is a beam which is simply supported, meaning pin on this side, pin on that side. We'll call that A, we'll call that B. The applied bending moment, it's not mmap this time, it's designated as MO, and this beam has some length L. So what's our first step? Our first step is to calculate the external loading, or to perform external equilibrium. So we do that here. and we designate an RA and an RB. We can just kind of pick them according to our intuition. Since, this M naught is going clockwise, kind of makes sense that, okay, maybe this roller side is going to be opposing that applied moment. And similarly, since this is going clockwise, if it's pinned here, that's very nice that it can actually provide a downward force, okay, to keep it on the ground. If we apply equilibrium in the vertical direction, okay, for the forces, what do we see? We would say, well, that's maybe a minus RA plus RB is equal to 0. So RA equals RB. When we apply equilibrium on the moments and we select, let's say, this point over here on the B side, okay, we can say, well, RB is no longer going to make any contribution, but RAL, okay, so acting that distance L across is going to be positive coming out of the board, while M naught is going into the board, is negative. So RA is equal to M naught over L. Now, this step is the same, or this portion of the first step is the same as what we've done previously. We will look at the shear forces at the ends of the beam and the internal bending moments at the ends of the beam. So let's look at the values at the left side. That would be A. When we do this, we have RA, okay, that's the external force that we've calculated out, and we have a V and an M, and there's no distributed load here. So when we look at RA and V, we know that, well, V is going to be equal to minus RA, and we know what RA is. So at the left side, we can say, or at point A, we can say, or very close to point A, we can say that the internal shear force is going to be minus M naught over L. Similarly, we can look at the bending moment, and there's nothing contributing to the bending moment here, and this distance is very small, so we don't have a moment arm to create a torque from this RA. So we have that this bending moment at the left side is going to be equal to 0. Now let's look at what's happening on the right side. We are now looking at B, or this right side, and we have this RB. We have internal shear force V and internal bending moment M. For the RB, okay, and the V, to balance out, what we need is for V to equal minus RB, or RB to equal minus V, however you want to look at it. And we know that RB is equal to RA. We know what RA is equal to, so we can say that this shear force is equal to M naught, or minus M naught over L. Similar to what we had on the left side, when we do analysis for the bending moment, we see that there's nothing contributing bending moment here besides this internal bending moment, and so that's going to be equal to 0. Now, that concludes step 1 of our methodology. What should step 2 look like? Well, it's modified just slightly. We're still going to be looking at creating a shear diagram, a shear force diagram. And we're still using, the differential or integral forms of distributed load and shear force. Okay, so that's the dV dx is equal to W. And now we've added this extra little bullet here saying, hey, delta V is also equal to FF. So if we happen to encounter a concentrated force being applied to the system, we can say, okay, there's going to be a jump in the internal shear force. Similarly, we have the opportunity to make a bending moment diagram, and we're going to use differential or integral forms of dm dx is equal to V. Okay, and again, if we happen to encounter an applied bending moment, there should be a jump delta M. Now in this problem, there's no discontinuity in applied force, right? There's nothing, but there is a discontinuity with this coupled moment that we've placed on this system. Okay, so this example is not going to account for, or we're not going to have to see a jump in the shear force, but we do expect to see a jump in the internal bending moment. So let's go ahead and continue. We're going to kind of copy our relevant parameters to the next page. Some of the relevant parameters will be, okay, what are the internal bending moment and shear force at the left side? What are the internal bending moment and shear force at the right side? As you see here, before we integrate. So now let's go ahead and use the integral form of dv dx equals w, right? So that dv equals w dx, and we then integrate w dx. So v is equal to w dx. This case, w is equal to 0. So what does that mean? That means it was 0th order distributed force, and that means we're going to have a constant, okay? So it's like 0th order, 0th order, okay? We still have 0th order. It's just a constant. And we need to satisfy the boundary condition on the left and on the right as well, okay? And so in order to do that, when we see this is 0, right? And it's equal to some constant. On the left side, it's got to be equal to minus m naught over L. On the right side, it's got to be equal to minus m naught over L. And that's good that they're the same, right? Isn't it? So that we know that C1 is going to be equal to minus m naught over L. And we can just write out that V is equal to minus m naught over L. So we come over here, and what are we going to plot? We're going to plot a line at minus m naught over L. Not particularly interesting, which is okay. It's nice when it's simple and it works out. What are we going to do? Let's do another integral. This time, we're going to really remember our relationship for dm dx is equal to v. And so we can write that m is equal to the integral of v dx. We go ahead and start putting down our axes. We perform some integration. So we know that v is equal to minus m naught over L. We're going to integrate this expression. And we're going to have another constant, let's say plus c, that will allow us to apply our boundary condition. So what do we see? On the left side, m of 0, the internal bending moment, is 0. Okay. Well, and you're like, oh yeah, duh, because the pin can't really apply any bending moment anyway. So it's going to be 0. The math also is telling us that it's 0, okay? So what does C have to be equal to? Well, x plug in x equals 0, this is 0. C is going to be equal to 0 on the left side. Now, that's nice, but as we move from the left to the right, at x equals L over 2, we have a discontinuity. So this expression doesn't hold for the entire length, okay, as we move across the beam. So we need to be kind of careful and maybe a little bit slick. We don't necessarily want to write out all these complicated expressions, but we need to know what slopes are, or what curvature might be if we have a second order expression. This is a first order expression, and know what to do when we hit these different benchmarks or these different discontinuities or these different locations where there might be some change in the loading. So we said at the left side, m is equal to 0. So we start there. We're having a negative slope, and we know that at x equals L over 2, something interesting happens. But we can go ahead, nothing's happening until we get to L over 2. So we can plug in x equals L over 2. And when we do that, what do we get? Well, we get L over L, and then we get a 2 in the denominator, so we get minus m naught over 2. Interesting, okay? So we go to this point, and now we know we have a discontinuity with this m naught being an applied moment coupled into the system, and that's going to cause a change in the internal bending moment. What's going to happen? This internal bending moment, okay, this change in internal bending moment is equal to m naught, and it's positive, so we're going to see a jump. We're going to see a jump up to a value of positive m naught over 2. Okay, so there it is. At x equals L over 2, we see this positive jump. My line is not perfectly straight, okay, but we see that delta m is equal to m naught. The slope has not changed, though. So this expression, this minus m naught x over L, or this slope of minus m naught over L, is still in place. Now, another thing we can look at is what is m at L? Well, it's also equal to 0, so we're here. So somehow we need to go from here to here, and the slope stays the same. It's still a first order expression, so we can conveniently draw a line, okay? And that's the complete solution, all right? We have a plot for the shear force as a function of x, and we have a plot for the internal bending moment as a function of x. And we don't necessarily need to have all the exact expressions to take care of these discontinuities and equations, but we do want to know what's happening graphically. And if we're asked, for example, to find the maximum bending moment, well, we'd be able to actually pick either this point or this point, because one's in compression, one's in tension. Actually, I guess I'm getting a little ahead of myself, but one's positive, one's negative here. Okay, let's leave it. We'll leave it at that. So now it's an opportunity to solve a problem. This one is a little bit tricky. I can't lie. Okay, it's a little bit tricky. It's going to take a little bit of time. All right, but what we're saying is that we have applied force and we have applied coupled moment, as you see here. And this one's going to be negative, or it's going to have a delta V that's negative because it's going down. This one is also going to have a negative delta but not in the shear force, but in the bending moment, okay, because this one's actually positive. Take a look at the methodology to do this problem. Be careful, and my request is that we analyze the case where this condition is true, when m app over L is greater than f app over 4. You're like, where did this come from? Well, as you do the math, you will be able to see why this relationship is important. And at one point, it determines if the slope is going to be positive or negative. And the question is asking, what is the maximum bending moment along the beam? I went ahead and I did this problem using or considering both of these loads in kind of the entirety of the problem. But if you wanted, you would be able to get the same solution if you use superposition. So you could also look at this as, okay, I'm going to create a shear force and bending moment diagram for just this load being applied to the system, and I'm going to create a shear force and bending moment for just this m apt being applied to the system. And you could add them together. I'm not quite sure, to be honest, which way is easier, because you've got two sets of diagrams that you have to superpose on each other, which is fine, okay? But you could do it that way if you like as well. So take some time to work on this, and this is the concluding question for our session. To conclude our session, though, just like to review what we started off saying. Our learning objectives were to strengthen our understanding for how to draw shear force and bending moment diagrams. And we were looking at equilibrium in part 1, and then looking at the differential and integral relationships, which include dv dx equals w, and also include dm dx equals v. And the goal here is to have this ability to kind of start to see what's happening inside structures with respect to the internal shear forces and the bending moments. And in particular, not just any structures, but we're talking what's happening in a transversely loaded beam. And this adds to our repertoire of being able to kind of see, hey, what's the internal torque in a shaft? Or what's the internal axial force in a bar? Well, I hope you've enjoyed this session, and I look forward to getting to talk some more about beams in our next session. Thank you.